All right, welcome back. In this week's video, we're going to get into combinatorics, which includes combinations and permutations. As always, we're mostly going to focus on the key visual intuitions or the insights that will make this concept make sense. And then the lion's share of the work of taking these skills and making them your own is going to fall on your own shoulders. You have to go and do practice, lots of questions, draw these diagrams out yourself, and really get that practice in. And that's to keep these videos at least to an hour and below as much as possible. As always, you can use 2 times speed if you are a faster learner. So 2 times speed or 1.5 is usually pretty good. This set of notes is going to be filled out a large part by some visuals that are going to be generated by the Combinatorics Visualizer app, and you can get a copy of that or access that by clicking the link down in the description. We're going to start off by saying that combinatorics is somewhat useful, and at the same time it's also not useful at all. So in your everyday life you're probably not going to use this that much, but in a math class it's going to be very, very important, specifically in probability. And so one of the things we can say actually is that probability is just combinatorics over n. This is a statement that you might see said by a teacher in a classroom. And we might not get into what that means, but hopefully as you go through combinatorics and then probability after, you'll kind of see why that statement could be true. The question that we're going to ask first, and hopefully answer by the end of this lesson, is just a simple one, maybe trying to, again, do something that we might actually see in the real world. This question that we're posing is, how many different 3-note chords can we create from 12 notes? And that's obviously a reference to the Western musical system. I am not a not a musical major or a what's it called? A musician, so I'm not super familiar with music notation and all that type of stuff, but this is the question we're trying to answer. And there's obviously other combinations we can look at. We can look at 4-note chords, 5-note chords, and so on, but perhaps you're just curious. Again, there's not really much of a purpose to answering this question, maybe just curiosity. Or maybe you saw the recent news article that a company created every possible melody using a computer. So creating every possible permutation of all the notes to create every melody, and then they copyrighted every single melody to show that copyrighting music is a silly idea. That was their kind of aim or their goal. So we're asking kind of a similar question, a little bit simpler, again, to focus on combinatorics. And we're saying, how many different 3-note chords can we create from 12 notes? How can we answer that question? So hopefully we'll get to that by the end of this video. We're going to start off by talking about permutations first. So we want to get into the idea, what is a permutation? And we'll keep it really simple because, of course, we are trying to introduce the concept slowly and not jump into the deep end. We can think about a permutation as a collection of objects that are in a certain order. And you might have seen or heard that permutation is where order matters. So, for instance, we could have something like A, B, and C. And we could ask the question, how many different ways could we rearrange these 3 letters? So that's our question. And we could start to list those out. We could say A, B, C, and B, C, A, and C, B, A, and so on. And let's go ahead and import a little image just to show what all those permutations look like. So we see here that we have 6 total ways of taking these 3 letters and rearranging the order. And so the question we have is, well, if we're looking at permutations, taking a collection of objects and rearranging them in different orders, what's the total number of ways we can do that? And what's our thinking that we can use to understand why we can go from something like 3 letters and end up with 6 total permutations? So here we have 6 permutations. And here we have 3 letters. I challenge you to pause the video and try to come up with a system of understanding why we're going from 3 letters to 6 permutations, and see if that system works for any number of objects and any output. Once you have an idea of how it works, you can then compare it to what we're going to take a look at next. So if you saw the last video over tree diagrams, you know that tree diagrams are a great way to think about all the possible outcomes. And we can also think that combinations and permutations is very similar. So we could say that if we have 3 letters, that means that we have 3 positions or slots that need to be filled. And when we think about this very first slot here, maybe we can do this in a color. We'll do green. This very first slot, we can put any letter we want from A, B, and C into this slot. And so what we kind of start to think is, well, that means that at the very beginning, we have 3 possible paths we can take. Our very first path is we choose the first object or letter, A. Our second path is B, and our third choice is C. And what we're saying here is that there's no repetitions, because we're only looking at ways that we can rearrange these 3 letters to form different words or sets. So we can pick A, B, or C, and you can probably see where this is going. This is our first set of branches, kind of like a tree diagram. And if we pick A, then we have some options to pick after A, right? So after A, we can say that our next possible letters we can pick would be B and then C. And then if we've picked B, we only have one option left after that, so it'd have to be C. And if we pick C here, again, this one would have to be B. And so we can repeat this for these as well. And let's go ahead and color code that. So this is, again, our first slot. And then we have our second choice for the first slot, so B. B can branch off now, and it can be A, or it can be C. And then if we have B and A chosen, again, we just have one choice at the end. So 100% chance that it has to be C. And here, same thing. This one has to be A. And we'll make our second slot magenta. So these are representing all of these branches. And then finally, down here at the bottom, if we were to pick C as our first choice, we again have 2 choices here. We could say that our next choice could be B or A. If we pick B, then it has to be A. If we pick A, then it has to be B. And we are doing this all out of order, but that's okay. So these again are all of our second slot, our second position options. And then finally, we have our last slot. We'll do that in a nice yellow. And that represents these final set of branches, which basically only have one choice, like that. So just with a simple diagram, we can see that the math as it works out is we have three possible options here in our first set of branches. Our second set of branches, there's two choices for each of those branches. And then finally, for each of those branches, we have one choice. And we hopefully remember from our tree diagram lesson that we multiply along the branches. And we add down at the end of our branches. And if it isn't already obvious, you know that this is really important, because one of the big questions we will see over and over again is, do we multiply or do we add? It can be a really hard thing to decide when we're working more advanced questions. What we see here is that for permutations, and for this example specifically, we're going to take our 3 in our first slot, and we're going to multiply it by our second slot, and take our second slot and multiply it by our first slot. And the reason that we know to do that is because, again, we're multiplying along our branches, and also because we can see that for this first choice, there's two choices, so 3 times 2. We know that that's going to give us all 3 of these choices multiplied by all of these here, and that's going to give us 6 total possibilities. Because these final branches only has one choice left over, then we just multiply by 1, and that gives us our final result. So what we kind of see is that if we have a collection of objects, in this case A, B, and C, so 3 total items, and if we're picking all 3, then the total number of ways that we can do this is 3 factorial. So 3 times 2 times 1. So if you haven't seen this before, factorial just means whenever you have a number, let's say that it's 4 factorial, in order to evaluate that expression, you take that number, you multiply it by the number that's 1 less than it, and the number that's 1 less than that, all the way down to 1, and that gives you the result of the factorial. So we can take kind of all this thinking and we can summarize it with this nice bit of notation, and we can say for any number of objects, if there's n objects, then there's going to be n factorial ways to rearrange those objects or rearrange those items like that. All right, what happens if we, again, keep it simple. We have 3 letters, A, B, and C. But what if we only pick 2 letters from the set? How many different ways could we pick 2 letters and rearrange them from that set? Take a second, as always, to try and come up with a method. Try to write them down first, and then try to see if you can explain why there's this number of permutations. And I'm going to go ahead, once again, and put the answer of all of the permutations on the screen. If you've worked it out, you should get a result that looks like this. And this is telling us that for 3 objects, picking 2, we get a total of 6 permutations, yet again. So let's see if we can understand why that's true, and see if we can come up with a formula for a case where we have 3 total objects but we're picking less than the total number. Once again, we're going to try to do this using a branching algorithm or a branching diagram or tree diagram, however you want to call it. So this time, once again, we're starting off and we know that we have slots or categories that we can put things in. So again, we're going to give our very first slot a color. This time we'll go with, let's say, red. And for our second slot, we'll go with green. And so we're asking the question, well, how many different ways can we pick our very first letter to arrange? And it looks very similar to what we just did. So what we can say is that our very first choice is going to be, let's put our A up at the top. Very first choice is going to be A. Our second choice is going to be B. And our third choice is still C. So far, nothing has changed, right? We're still looking at the same outcomes for the first choice. We have 3 total choices here. And you've probably already worked out the rest of this. It's very similar to what we just saw. In our next set of branches, we again have 2 choices. So what we see for our very top branch, we can say that the next one could be B, and it could be C. Here, we could have A, and then C. And then here, we have B and A. And because we're only picking 2 this time, that's where our branching diagram stops. And we've now shown all the possible ways that we can have 2 objects chosen from a set of 3. And let's go ahead and highlight the second set of branches. So we get this. And this gives us the full mapping of the problem. Once again, if we want to see the total number of choices, we can see at the end 1, 2, 3, 4, 5, and 6. We get 3 times 2, and we get 6 permutations. Can you see what the pattern is from the question that we looked at before to this one? Hopefully you'll notice that this is again the total number of objects, and then we're we're doing factorial of that number. So what we can say is that we're doing 3 factorial here, and we're doing 3 times 2, but this last number here is 1, and it's no longer being considered, so it's just 3 times 2. So how could we take this result? We saw this one up here. This was 3 times, where did it go? 3 times 2 times 1. And then down here we saw this was 3 times 2. And we probably have a pretty good guess of what's happening. We could probably write down a formula, but if not, we could do one more example. We could say, well, what if we had 4 objects and we choose 3 to permute? Well, we'd say, oh, we have 3 possible categories or slots here. And we're picking 3 things. So the very first thing, we have 4 things we could pick from. The next we could pick 3, and then 2. And so what we kind of notice is that we're doing the factorial, but we're kind of cutting off after a certain number of slots. So whatever this number is here, for instance, if it was 2, like that, then we just not consider that one. So we need a formula that kind of represents all of that understanding and thinking in one place. So that brings us down to the permutation formula. And the permutation formula is NPR So we'll start off with the math notation first. N, P, R. Top part of our formula is, well, before we write this, actually we should say, what is N? N is the total we can say R is the number picked or chosen from the set. And this NPR, we can say this as N permute R. I don't know if that's official way of saying that, but that's how I pronounce it. And we're saying that whatever these set of numbers are, we notice always in our formula that the total number of objects in factorial is important. So, excuse me. If again we go back to our case we looked at before, we have A, B, C. We notice that we had 6 total options: ABC, CAB, CBA, BAC, BCA, and ACB. So we started with 3, and then our formula was 3 times 2 times 1. So here we're saying N is equal to 3. So we know that N factorial has to be somewhere in our formula. Now the tricky part comes when we do something like ABC. Oops. But this time we're picking only 2 out of those 3 objects. In that case, we know that again, we're going to have 3 times 2 times 1, but we need this last number to somehow cancel out or not be considered. And so to do that, what we do is N minus R factorial in the bottom. What does that look like? That's kind of abstract, right? If we were to actually apply that, again, to this case down here where we have 6 cases: AC, AB, BC, BA, CB, and CA. Up here we can say, well, we know, again, that there are 3 total objects, so 3 times 2 times 1 are N is 3, that's the top part of our formula. The bottom part is now 3 minus the number of objects that we chose, which is 2, like that. So 3 minus 2 factorial. And so when we do that, we get 3 times 2 times 1 in the top. And in the bottom, we just get 1 factorial. And following rules of division, we say, well, we have a common factor in the top and bottom, and so it cancels out. So kind of like we were saying up here, this last one is not considered because we only have 2 possible slots. We adjust for that in our formula by putting this N minus R factorial in the bottom of our formula. So this little change that's happening there is reflected by the N minus R in the bottom of the formula. And so that gives us our final result. We say that for any permutation where order matters, if we have N total objects and we want to grab a certain number of those objects, R number of those objects out of that group, we're going to get this formula N factorial over N minus R factorial. Just like that. And so that is permutations. A very quick introduction, of course, but you can now solve any question that's asking about how you can rearrange objects and calculate the final result. Alright, that brings us to combinations. For combinations, we can say the opposite of what we said above, and we can say for combinations, order does not matter. So you might have heard this previously. Order doesn't matter. What does that mean, or what does that look like? Okay, so what does it mean that order doesn't matter? Let's go back to our example above. We had, again, keeping it very simple, A, B, and C. And we're asking the question, how many different ways can we rearrange these letters to form different groups of those words? And we found that in total, there were 6 total permutations. But if we think about that as a grouping of objects, we can say that every single one of those is actually the exact same group. So this might be silly, but we're going to switch over from maybe using letters to something that's probably more memorable, even if it's silly. And we're going to say we're building a sandwich. We are going to make a sandwich, and this sandwich has 4 ingredients on the list. The ingredients are lettuce, tomato, cheese, and bacon. And let's see if we can copy and paste this in. There we go. Awesome. So here's our ingredients list. And just like before, we can ask the question, how many different ways could we take these 4 objects and rearrange them? And if you want to, of course, you can take a moment to try and sort that out, see how many permutations there are using the formula that we just learned. Hopefully, what you'll find is that in total, we get a diagram that looks something like this. And what we can see is that our formula, as we calculated it above, is n permute r is n factorial over n minus r factorial. And so in this case, Rn is 4, Rr is also 4. We're picking all 4 of those items. And so we get 4 permute 4 is equal to 4 factorial over 4 minus 4 factorial. That gives us 4 factorial over 0 factorial. And we've agreed, as a matter of convention, that 0 factorial is 1. So we get 4 times 3 times 2 times 1 all over 1. And that gives us 24 possible permutations. Like that. Now, in the context of a sandwich, you're probably already thinking, it doesn't really matter, right, how we organize these ingredients on, well, or in between 2 pieces of bread. And so what we hopefully see here is that this is indeed not very useful. There might be cases where a recipe calls for ingredients to be placed into the recipe in a certain order. A sandwich is probably not one of them, though there's probably some people in the comments who might get a little bit upset about that statement when it comes to cheeseburgers having the meat, cheese, and lettuce in a certain order. In that case, you can, by all means, say that one of these permutations is the correct one. But for our purposes, we kind of see that out of all of these permutations, they're all the same. So in a way, we can say that there's only one combination here. And this isn't really a super great way to talk about combinations because, again, we're using all the ingredients every single time. But let's say that we tried this again and we said our ingredients list, maybe we should copy that. Our ingredients list is once again lettuce, cheese, tomato, and bacon. And this time we want to only choose 3 ingredients to make a sandwich. And as a matter of practice, can we calculate how many we would have if we're only picking 3 of these from our set of objects? Take a second to calculate that out. You should have 4 permute 3 And this is our final results list. This is all the ways that we can choose 3 ingredients from a set of 4 objects. And it turns out again that this result is also 24. Now again, this is also kind of silly. We see that all of these in our very first row is the same sandwich. And likewise for here and for here, that's also true. Those are the same sandwich, they're just reorganized. So the question we ask is, when order doesn't matter, how many unique groupings do we actually have? Just from this diagram, it should be pretty obvious that we can see if this whole top row is all the same thing, and this one here is also the same thing, and same with the third and the fourth row, we only have 4 combinations. And maybe you're already starting to think about a formula that we can come up with to account for this change, where order doesn't matter. What is our total outcome? And let's go ahead and update our diagram to reflect that out of these 24, only 4 of them are unique. So we get something that looks like this. And we say, well, our permutation formula works pretty well. We just need to modify it to account for the fact that some of our results are duplicates. And the question is, well, how many duplicates are there for each of these unique groupings? And you might go, well, isn't this first row permutations of this group? So all of these are permutations of tomato, cheese, and lettuce. And so the question is, how many permutations we have? Well, we have 3 objects in total, and we're permuting them in all the possible ways. So that's 3 times 2 times 1. So we have 6 of these, and only 1 of them is unique. So what we can say is that we need to take our results and divide this by all of the possible permutations that can come from one unique grouping. So each of these is going to have 3 factorial permutations, which, again, are the exact same sandwich. So it turns out for our combination formula that we're just taking our permutation formula, which we saw above, and we're just modifying it a little bit. So this is our permutation formula. We now just want to divide everything by the number of items that we're choosing. So for instance, we have up here 4 total items. Because we chose 3 for our items, there's going to be 3 factorial ways for each of those unique groupings to permute. But we don't care about the permutations. We don't care about the different orderings. We just care about the unique groupings, where those are each special. So we get a formula that looks like this. Now, we should say here, you don't have to hold all of this in your head. So this is really just an explanation to see where the formulas come from, why they make sense. When you're actually working with permutations and combinations, you will not be considering all of this math and logic. You're just going to decide, does order matter, does order not matter, and then you're going to apply the formulas and solve your problems, as we'll see down below. All right, so that brings us to our formula for combinations, which we kind of already see. So the combinations formula And what we can say here is that n CR, C now for combinations, is equal to n factorial over r factorial n minus r factorial, like that. This is pronounced n choose r. So that right there is pronounced n choose r. So if we have, like we saw up here, 4 objects total and we chose 3, we're saying 4 choose 3. All of this notation in English will get easier with time, as we'll see lots and lots of practice, lots of homework. But this is again, just the visual intuition, what's happening when you're looking at a question that could be working with permutations or combinations. All right. Oh, there we go. Let's get into our question that we asked at the beginning of the video. Our question was, how many ways can we create a 3-note chord from a 12-note system? All right, so practice question number 1 is having us answer the question we asked at the beginning of this video. How many ways can we create a 3-note chord from a 12-note musical system? Take a second to try and answer this on your own, and then we'll get into the solution. The very first thing that we have to establish is the set that we're talking about. So I know that we could say A and A sharp and things like that, but to keep it simple, we'll use letters and numbers. So let's do 0 through 9. We'll say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's 10 notes. And then our last 2 we'll say is A and B. And the question we have to ask is, does order matter? If we think about a chord, maybe it's F sharp, A, and B. Is this a different chord than A, B, and F sharp? And I, again, cannot answer this question. I am not a musician if these are considered unique chords, but this would be the first question that we'd have to decide on. So we can say order might matter. And we could also consider other things. What if we're bringing notes from other octaves and things like that? But we'll consider both cases for this question. We'll say when order does matter, hopefully at this point we're thinking, well, this is a permutation. And the next question we ask is, well, how many objects do we have in our set total? We say there are 12 notes. So we can say our n is 12. We can say that the number of things we're choosing out of that total set of 12 is 3. And so if order does matter, for instance, we're saying the F sharp A, B, so we're pulling notes from different octaves, then we'd get 12 permute 3. And so we get 12 factorial over 12 minus 3 factorial, like that. And then we could simplify down, and we'd say this is 12 factorial over 9 factorial, or 12 times 11 times 10, like that, which would be 120 times 11, and we could calculate that out. Maybe it's a couple hundred or so. And then we also ask the question, well, in the case that order doesn't matter, in that case, we would call that a combination. Our value for n does not change, and our value for r does not change. And so we get 12 choose 3, and so we get 12 factorial over 3 factorial, And then again, 12 minus 9 factorial. So this exact same result, excuse me, but now it's being divided by 3. And so in that way, we get all the cases, again, where the groupings are unique, and then we get all the cases where the order is unique. Let's take a look at what that could look like. And we're going to put both of those results up on the screen. This may or may not show up clearly at 1080p, but hopefully we get to see here that in total we have, let's see, actually, that's 1320 permutations. And then out of those, we have 220 unique groupings. Oops. 220 combinations. Okay, so again, very simple, but satisfying a little bit of silly curiosity maybe to answer this question. I feel like there's a lot to actually think about with this. Like we mentioned, pulling from different octaves, if those count as unique chords, might be a good topic for a math IA. Okay, so that is a quick practice question for permutations and combinations. Let's take a look at something that is a little bit more challenging. This brings us to practice question number 2. We can see here that we are considering a group of students, 14 in total. Some of those are girls, some of those are boys, and we're trying to find the total number of ways that we can form a team of 5. So we can write that down as our first piece of information. We have a team of 5 students. And this team has to have 2 girls and 3 boys. Take a second to kind of work that out and think about it. Maybe try to come up with some solutions on your own. And then we'll get into the solution. So, one way we could approach this there we go. One way that we could approach this is to kind of brute force and write down every possible team, look through all of those possibilities, and find the ones that meet these conditions. There's nothing wrong with that approach. It's just quite slow. And of course, on a test or just out of laziness, we would probably try to do it a more efficient way. One of the ways that we can do that, of course, is to use combinations and permutations, since that's the topic of this video. What we can say is that we can start with our first condition. So we first think about the case where there are 2 girls. And we say, well, if there are 2 girls on the team, how many different ways can we put 2 girls on this team of 5? So first thing we can do is we can put our positions or our slots in. There's 5 total slots. And these first 2 slots, we're going to designate for the girls. Which means, of course, that the last 3 slots have to be boys. And what we can say is that if we have, again, 8 options, and we have 2 choices, well, we can say that our R is 2 and our N is 8. And the only question we have to answer then is this a permutation or a combination? And when we say, well, if we put, girl 1 here and girl 2 here, is that the same as girl 2 and girl 1? We say absolutely. Order does not matter for this team. So to find out the total number of ways that we can fill these first two slots, we can say 8, choose 2. So this slot right here is going to be 8, choose 2. And it's a bit weird because before we were putting a single number in one slot, and now we have a number to represent both of these slots here. And then we do the same thing for the boys. We say, well, how many ways could we fill in these 3 remaining slots with boys? In total, there's 6 options. And in our number of choices, we have 3. So we can say that our R equals 3, our N equals 6, and this can be represented by 6, choose 3, like that. And this brings us to a question that we ask a lot, and it's a question that we said we would ask at least one time by the end of this video. And that question is, do we add or multiply? So right in here, is this addition or is it multiplication? We still need to calculate, of course, what 8 choose 2 is, and we need to calculate 6 choose 3. But the really big question here is, once we have those results, do we add or multiply here? And so if you're having that question, one of the things you can do is you can try both adding and multiplying and seeing which number looks more reasonable. So we could try that, we could call that like a guess and check method. Try both and see which one's more reasonable. But probably a smarter way to approach this is to instead think about where we are in our branching diagram that we saw before. So if we're thinking here, all of the places where we picked 2 girls, that means we have a really big tree diagram, and we're not going to, of course, draw the whole thing. What we say is that for this very first choice of student, we actually have 14 branches, and just thinking about that is a lot. So we're just going to draw kind of a rough representation. We say here we have 14 choices. It could be all the boys and all the girls, but we're again saying the first 2 slots are girls. So we're saying this one could be a girl, and there are 8 girls in total. So 8 of these first branches, and we need a lot more branches in here. Maybe we should draw those in. So 1, 2, 3, 4, 5, 6, 7, and 8 are all going to be girls. And then 5 of those branches, 1, 2, 3, 4, and 5. This is sufficiently messy, which is probably what it will look like if you try to do this yourself. So 5 of these are going to be the boys. And what we're saying is, we're thinking about all these branches here. The first one's a girl, and then the second choice is also a girl. Now each of these branches here is going to have 13 possible choices. And so we're trying to, again, not draw all this out. So 1, 2, 3, 4, 5. And we're just going to try to sketch this without doing too much work. We have another girl. And then once we pick those first 2 girls in this branch, we then have to pick 3 boys in succession after that. And so what we kind of see is that these choices are falling after each other within our branching diagram. And if they fall after each other in the branching diagram, it means that we have to multiply again along those branches. So like we mentioned before, if you're wondering if it's addition or multiplication, think about where those choices are happening. Are they happening inside of this branching diagram, or are they happening at the ends of the branches? We'll see a case of that in the second part of this question. In this case, what we see here is that we're multiplying along those branches, and so when we give these 2 options for the first girl and the second girl, Then we get our three options for boy 1, 2, and 3. We're going to have to multiply those all together to get our final result. Let's go ahead and get numbers for that. So 8 choose 2. Let's see what that ends up being. Eight choose 2 is 28. And our next one is 6 choose 3. We get 20. So in total, we get 20 times 28. And that gives us a total of 560 teams as our final answer for the first part of this question. So 560 teams is our final answer. Again, we can see that for all the 20 possibilities or branches where we pick two girls, there's going to be 20 combinations on each of those branches. So we multiply them together to get our final result. Okay, let's jump into the bottom result, or the bottom question, which is a little bit more challenging. What we can start off by saying is that this is asking about more than one condition. So our team size is a little bit smaller this time. We have in total 3 positions to fill. And in this case, we're saying at least one boy. So the very first case is that we're going to have a boy here, and then a girl and a girl. In our second case, we can also have 2 boys and 1 girl. And then finally, our last case is a team of all boys. All 3 of these conditions meet what the question's asking, which is to have a team with at least 1 boy. And so each of these is its own subproblem that we have to solve, and then when we get the results for that, we have to combine all those results together to get our final result. So to do that, let's visually organize this as well. Let's take our first case, girl, girl, boy, and we'll move that. We'll try to move that. All right, starting with our first condition on the left, we have girl, girl, boy, and we want to see how we can calculate all the possible combinations for that case. As is up above, order does not matter for these teams, so we know it's a combination. We start off with our very first grouping. We say 2 girls out of 8, and so we can say that here, 8 choose 2, and here we get 6 choose 1. Again, we saw from above, that's multiplication. 8 choose 2 is 28. So we get 28 here. And 6 choose 1 is 6. So if you have 6 objects and you're grabbing 1 out of them, there's 6 ways to do that. We multiply that together and we get a final result of 28 times 6 is 168. So there's 168 teams where there's exactly 1 boy and 2 girls. We can repeat this process for our other 2 cases, and what we would see here is that this is going to be 8 choose 1, and this is going to be 6 choose 2. We get 8, 6 choose 2, is 15. And 8 times 15 is 80 plus 40 is 120. And then finally over here we have a group of all boys, and so we say for this one we have 6 choose 3, and 6 choose 3 we did above, and that ended up being 20. So we know here there's 20 teams. So we have these 3 separate scenarios. We get a result for each of them separately. And then, of course, we ask the question, do we add or do we multiply? And hopefully you have an answer, kind of using the method that we talked about in the first part of this question. What we can see is that for these results, if we were to again put them onto a branching diagram, what we'd see is that these results, these teams that we're getting, they are full complete results. So we've walked through the branching diagram, which has a huge number of possibilities, 14 choices to start out, and then 13, and then 12, and so on. And what we can say is at the end of this massive tree with so many branches, these results that we're getting here, here, and here are ends, or it's the final part of this branching diagram. And so these 168 teams we see here are 168 branches that we see in this branching diagram. Our next one is 120, and our final one is 20. And so because, again, we're at the end of this branching tree diagram, we're adding these together. So this is not a multiplication, this is an addition. And we add these results together, excuse me, we get 140 plus 160 is 300 plus 8. And that gives us a total of 308 teams. Again, that meets this initial condition of at least one boy, where that's the case of all boys, 2 boys, or 1 boy. And so this is our final result. Okay, so that's kind of doing it how you probably do it on a test. Now, again, we have tools to visualize this and see all the possible cases. So let's take a look at what that might look like. There we go. That's not bad. Okay. So if we were to brute force this, we could come up with a total list of combinations that look like this. And this might be silly to do in any scenario, but what this kind of does is it shows us that if we consider one of our cases, for instance, if we take a look at this case here where there's all boys, we could go into the full combination list and we could start to highlight those results. So we could say, well, there's a case there. Yeah, let's use a different color. Maybe yellow. That's much better. So we could go through here and we could highlight all the cases where there are only boys on a team. And in total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and we need one more. Feels like we're doing a crossword puzzle. 20. So we can see here that there are indeed 20 teams of 3 boys. What's the purpose of doing something like this? Well, it gives us a visual idea of what it looks like. And when we're on a test working through questions, we don't actually have this type of image in our head, but we have a vague idea of this being in our head. And what that tells us is that when we see these 20 teams, those are separate results from the other 2 scenarios, 120 and 168. And what that's good to know is because, again, it asks us this question. And that's good to know because it helps us answer this question, is it addition or is it multiplication? We can kind of clearly see that if we're able to visualize this in our minds, roughly speaking, are we at the collection of final teams or are we somewhere in our branching diagram, whether we should add or multiply? So that's kind of the visual intuition we should try to keep in mind when we're solving these questions and we're unsure if we, again, are using multiplication or addition. All right, that brings us to the end of practice question number 2. Let's do a quick recap. All right, so this is a pretty simple video in that we really have 2 main ideas. We have combinations and permutations. Permutations is when order matters, and combinations is when order does not matter. We saw that for permutations, we have this formula NPR, where N is the number of objects in total, and R is the number of objects we're picking out of that set. Then we saw the case for combinations where order doesn't matter. In that case, we have the formula NCR, or N choose R. And again, N is the total number of objects, and R is the number of objects we're pulling out of that set. We worked through a first practice question, taking a look at when order does and doesn't matter. And then we took a look at a second practice question where we might ask the question, should we add or should we multiply? And how do we know which one to do when working through a problem? There is something that we have not talked about, and it's pretty important. And what we can say down here, maybe in final thoughts, is that combinations and permutations do not work for everything. So what we can say is that combinations and permutations don't work for everything. One of these cases would be the case for a combination lock. A combination lock usually has the numbers 0 through 9, and it might have maybe 4 slots available for each slot. And what we see for this is that we can repeat numbers. So this is repetition allowed. And in those cases, if we were to do a branching diagram, we'd see that the first one, we have 10 possible choices. So we put a 10 there. And in our next number that we could pick for our combination, we have another 10 numbers we can pick. And that's true for all of these slots. And so for this case, our result's pretty easy. It's just the number of positions or slots times the number of choices in each of those slots. And so we can say 10 to the 4th power, or 10 times 10 times 10 times 10, like that. Another case of this might be something like a license plate. So here in California, we are running out of license plate numbers, and license plate numbers here in California, I believe, are a number, and then it's 3 letters, A through Z, and then it's 3 numbers. And again, this is a case where repetition is allowed. So we're not pulling objects from a set. We actually have an unlimited number of those things. We could say here, we have 10 numbers we can pull from. We have 26 letters, 26 letters, 26 letters, 10, 10, and 10. And so the total number of license plates that we could form using this type of pattern would just be taking those and multiplying them together. So that would be 10 to the 4th times 26 to the 3rd, which is some really, really large number. And that's how we have enough license plates to serve, a population that's really, really large here in California. So this is just something else to keep in mind. Combinations and permutations don't work for everything. And you really have to decide whether the pattern that it's following is something that looks like a combination or permutation, or if it falls into this kind of other miscellaneous bucket. Okay, that brings us to the end of this lesson. If there are mistakes that you caught, if you have questions you'd like to ask, put all those down in the comment section below. As mentioned before, these set of notes are going to be available in the comment section down below, and also the Combinatorics Visualizer app you can also click on and explore. That will be linked below as well. Alright, I will see you in the next one.